Welcome to the second video in our Class 19 series of lecture videos. In the first video, we looked at retrosynthesis in order to try to devise a methodology to synthesize a more complex molecule from simpler molecules and reactions that we're familiar with. So we'll begin this video with considering the retrosynthesis of a ketone. We could, of course, synthesize our ketone from the oxidation of an alcohol, and we could think about creating this alcohol either by cutting bond A, B, or C. So if we cut bond B or C, we would be doing a Grignard reaction with some sort of carbonyl carbon, either butanal or acetaldehyde. And if we cut bond A, we would be presumably oxidizing something, either that or doing an SN2 reaction or an SN1 reaction on some simpler hydrocarbon. So we envision different approaches based on three different disconnections, A, B, and C. So it's useful to have a basic set of reactions and knowledge about which ones might work well and which ones might be challenging at the set of your fingertips. And so, of course, you study and practice to get those, ideas down. So continuing, further reactions of alcohols and ethers. This is chapter 9 in our text. Some of this material you're familiar with, and it's good review. So an alcohol under acidic conditions can undergo SN1 or E1 reaction mechanisms. We'll take tert-butyl alcohol. If we added concentrated HBr, well, we'd protonate our hydroxyl group. It would then leave as water, generating a tertiary carbocation that would be substituted by our bromide anion, which is a good, nucleophile. And so we favor our SN1 product. Again, we're knowledgeable that there's E1 mechanisms going on at the same time. If you create this tertiary carbocation, instead of allowing bromine to substitute in, which it will do most of the time, your water might pull a proton off of an adjacent carbon to that carbocation center, and in the process create an alkene. And so this is our E1 product, and yes, we get H3O plus and Br minus. All of these reactions are reversible, so in theory you could protonate your alkene to generate a tertiary carbocation, and then bromide could add in again. So yeah, Le Chatelier helps drive us in one direction or another, and sometimes we can do things to favor one mechanism over another. So let's refresh our minds on that and review. Let's see, the point is you must turn the alcohol into a good leaving group by protonation. To favor E1, we use aqueous acidic conditions with H2SO4, that is, an acid whose conjugate base is a poor nucleophile. So we'll protonate our alcohol, it will leave as water, and now our HSO4 minus is not a good nucleophile. Of course, water could just add back in, and that would be like SN1, but we'd be going backwards. It's Le Chatelier that helps drive us to this E1 product. Because why? Because typically when we do something like that, we either do it in such a manner that we can boil off our organic product, or we can remove water as it's formed. So in this case, it might be easier to boil off our 2-methyl propene because it's going to have a lower boiling point than tert-butyl alcohol. And if you take this out of the mix, then you cannot go backwards. We'll see in our chapter on alkenes that we can indeed protonate alkenes with strong acids like HBr, or in this case H2SO4, which dissociates into H3O plus and HSO4 minus. So in theory, we could go one way or another, and it's only Le Chatelier that helps drive us in one direction. And like I said, if we really wanted to favor the E1 product, we would remove it as it's formed. So, continuing forward, Compared to the starting material, the E1 product has lost water. We call such a reaction a dehydration. Here's one that you might actually do in lab. We have cyclohexyl alcohol, or cyclohexanol, and we throw in sulfuric acid. We heat this. Ultimately, you lose water and you generate cyclohexene. In our lab, I think we'll be boiling this off and collecting it in a Brinkmann distillation head. So that's a little bit of review of our SN1 and E1. Here's something new that we can add to the mix. One could synthesize an ether by substitution of an alcohol solvent instead of water. So here we have our H2SO4, and now instead of doing this in aqueous conditions where we have water present, we have excess methanol present. So what's going to happen? We're going to protonate our hydroxyl group. It's going to leave as water. There will be a small amount of this versus what? An ocean of methanol. And now we're going to favor SN1 because before, when we were in water, yes, we would still quote unquote favor SN1. The water would add back in, but we'd just be generating our starting material again. Instead, we're in methanol. So we notice now when we do SN1, our methanol adds in. We deprotonate the molecule of methanol that added into the tertiary carbocation, and lo and behold, we have methyl tert butyl ether. That is the SN1 product. We still get some E1 byproducts, but we're actually going to favor SN1 under these conditions with the methanol versus dehydrating our tert butanol carbon framework. And yes, at the other end, we get protonated methanol and HSO4 minus. And like I said, we have a minor E1 byproduct, but now our SN1 is favored because, again, we've got methanol and we can distinguish it from our starting material. If this is complex, this is definitely something we want to chat more about, either in the class time, office hours, or we can ask our SI about it. So that pretty much ends our second video. Good luck with the question, and I'll see you in the next video.